Okay. Sorry for a late start here. Just making sure that everybody up here has their everyone who's actually shown up here has their test back. Um, okay. All right. So I unfortunately I do need to continue covering things, but I will say a little bit, at least in general terms, about the exam. Um, so overall, the average was a 78 and a high 94, but that includes everybody, um, including graduate students. Of course, I would hope raise things a little bit. Um, so if we limit that to undergraduates, the average dips some to like a 74, and the high 90. Okay, and um, okay. Um, all right, so a few things that come to mind with regard to some of the most common issues with the problems. Of course, three of the five problems dealt with the error formula for polynomial interpolation in some way. So, um, so the thing is, the procedure for working problem number one in particular, that's something else described on a practice test as well as on the just during a review, needs to find maximum in absolute value of okay. Of fn plus 1 at an unknown point. So the thing is, in some of the problems, an x value for the error was given, so problems 4 and 5. But that would not apply to this part. The error formula says that the error includes the n plus first derivative of your function at a point you simply do not know. All you know is that this point lies within an interval containing interpolation points. So that had to be done using Calc 1 procedure. Find critical points, check endpoints. And so there were not many cases where that whole process was successfully executed. For a function given, it seemed that some Cal 1 skills had been lost. So for that function in question, the product rule was needed to compute the appropriate derivative. And in the problem that he had, n was equal to 1. So you needed the max of f double prime. But that means whatever you have there, you need to take one derivative more to see if there were any critical points. And then in that case, you also check the endpoints, which would be the extremal interpolation points. But I see how some had the right idea, but messed up somewhere along the way. Okay. Also needed the max of x naught 1 x minus xn. And here again, critical points. Here the endpoint's not needed, because at the endpoints you know it's 0. So that was the key to getting the error. It just seemed like there are a lot of like algebraic mistakes or mistakes in lower level skills that prevented people from getting full points on that problem. Okay. Okay. Problem 2 was the one about convergence. So if your function f of h goes to converges to some limit f naught, and in this case the limit itself was given, you need to check how this difference, f of h minus f naught, goes to 0. So what some people did was like they would correctly substitute the Taylor expansion that was needed, but forgot to take the limit itself into account. You have to subtract that off, and then see how things go to 0. And a number of people got this problem right, so that's good. But again, there were some slip-ups in the process. Okay. Number 3 went pretty well. Most people, this is about the floating point arithmetic issues. Most people got the correct modification. Where they did not, again, there's some algebraic mistakes. And the other part of the question was, you have a function of x. For which values of x is there an actual problem? So more than one answer was acceptable. So problematic x not identified. Either it was left out, or we put in a value of x. Like for instance, an expression isn't even defined. So like for example, this particular expression, if you plugged in x equals 0, you would not get a real number. That's something that would not have led to the floating point arithmetic issue at hand. So now, values close to 0 were the problem on the practice test. Doesn't mean they're going to be in the real test. Okay. Okay. But I think generally the class as a whole did better on that problem. Number 4 is about Lagrange interpolation. So I think the single biggest problem with this one was it's hyperbolic cosine, not cosine. That's not a factorial, by the way. That's an exclamation point of frustration. So not excitement like in yesterday's class. So yeah, for the most part, everybody was forming the Lagrange polynomials correctly, so that's good. But then putting y values in there, sometimes the y values were left out altogether, or something very strange was put down there. Also, not taking derivatives correctly. So derivative of e to the x plus e to the minus x over 2 is actually easier to compute than a lot of people seem to think. Because derivative of e to the x is e to the x. And the derivative of e to the minus x, you just have a minus there. Another way of putting it, this is hyperbolic cosine. That was the definition was given. This is hyperbolic sine. The derivative of also cosh and sinh. The derivative of cosh is sinh. The derivative of sinh is cosh. It's like how cosine and sine, you take derivatives that keep going back and forth, except it's even simpler because there's no sign change to keep track of. Yeah. Okay. And then for the last one, Newton interpolation. The most common mistake, okay, well, two mistakes in particular that were pretty common. In a divided difference table, you must divide by a difference of x values. So in your table, you have these divided differences, and people were subtracting them, but they were forgetting to divide by the difference of appropriate x values that went with them. There's a reason it's called a divided difference. You are dividing differences. Okay. Also, for a function in question, you need to take a derivative for the interpolation error. Required the chain rule that was forgotten. So, for example, if you have a function of something of this type, sine ax, where a is a constant, the derivative of that would be cosine ax, and what am I forgetting? I have to multiply by a. I'll put it out front. Whoops. Okay. So in certain cases, that was forgotten. Okay. The whoops. Dang thing. All right. As far as the lightning round is concerned, that went fairly well in terms of the answers that I got. And I was pretty flexible as to what I would consider an acceptable answer. Okay. I'm flipping through to see if there's anything in particular. Okay. So without referring to a particular problem, just a couple reminders. If you're given n plus 1 points, interpolating polynomial has degree n. So it's always one less than the number of points you're given. So a question related to that, a surprising number of people got the degree wrong in that one. Okay. Also, properties of barycentric interpolation and Newton interpolation were confused with one another. So Newton interpolation, the advantage of that is you can add interpolation points quite easily and preserve the work that you did before. Okay. Barycentric, since it's a form of Lagrange, adding points is more tedious, but it does have the advantage over Lagrange that can reuse information for evaluation of your interpolating polynomial to cut down on what you need to do as opposed to just using ordinary Lagrange polynomials directly. Okay. All right. So if you have any questions about how the test is graded, you can contact me individually. Students on the coast should have received an email that had a scan of your graded test. I apologize if it may not be very readable. I actually have not received the hard copies of your test. Dr. Cole scanned them and sent them to me the next morning, and that's what I graded. So what you're seeing is through 2 layers of scan, so it might not be very readable. But I will get these back down to the coast and get them to you somehow. Okay, so but you have regular problems, 12 points each, so 60% of a test. And I'll give certain levels of partial credit depending on how much of a process you completed. Lightning round problems, 40% of a test. So those problems were those questions were 4 points each. Okay. So the a midterm, 30% of the grade. With the final will be 40%, and there's still several homework assignments. Okay. Okay. Now, I also want to say something about what I've been doing the last couple of assignments with grading. So for recent homeworks, let's see, I guess it'd be homeworks 4 and 5. So I am using scripts, MATLAB scripts, and what these scripts do is to save time during grading, to run your code and check the output. So the functions that you're assigned to write for some of these problems have to return a certain output. So I supplied input. I have on hand what the answer is supposed to be, and I check it against that. So what my script will tell me is, first of all, is a file even there? Because in some cases it's not, if it was not turned in. Or if a script tried to run it, but it crashed, there was some sort of MATLAB error that happened. Or if it does produce an output, then it'll show me that output, and it'll show me what the output's supposed to be, so I can compare. It'll tell me if they matched or not. Now, I don't just leave a grading up to my script. That would be bad. So I actually do look at the output that's generated. So in some cases, the student did produce the correct result, but it was maybe not in a format not expected, so I would still give credit in such cases. So what I will do is I will post the scripts used for recent assignments I graded, homeworks 4 and 5, so you can see what was done. And for upcoming homeworks. So what you can do is you can try this out on your code before you submit it, and get an idea if it's working or not, and what kind of output is expected. So I still need to do that for the upcoming assignment, homework 6, which is on material that I'll start. Well, actually, it's the last material from interpolation and material that I'm going to start covering today. Okay, so yeah, so these scripts, they provide a sample input and basically answer a key. Now, if you're going to try to cheat and have it simply generate the expected output, I'd reserve a right to change the input and output when I grade it. So don't try that. Also, since the final exam will also have a lightning round, please remember that my BS detector is always switched on. So, okay. So these will be posted on the assignments page. Okay, and let's see. Also, for the next assignment, homework 6. Okay, so that's on the last chapter, oscillatory or Hermite interpolation, that I covered before the midterm. And then the section I'm going to cover today on differentiation. So one thing I want to point out is one of the problems in section 9.1. Okay, so exploration 9.1.5 relates to solution of 9.1.2, which is a problem that is not assigned. So what I will do to work around that is solution to 9.1.2, which is just a MATLAB. It's a MATLAB coding problem. Will be posted on the assignments page. So before anyone freaks out that I'm expecting someone to do something that's outside the assignment, I am not. So that'll even be made available to you, and I actually have it open in MATLAB today to give you a look at. Okay. So just so you know, when you get to this problem, or this problem, what's going on with that. Okay. Okay. For homework 5, handful of people have turned it in. Hopefully more will soon, so I can get those back to you. Okay. Yes.
Will you upload the solutions to the test?
No, I will not be doing that. I cannot. I have my reasons.
So like if you come to the confession.
Yes, yeah, that's why I want people to contact me individually. Then I can talk about anything. Yeah. Okay. Alrighty. And at some point, I don't know exactly when yet. Generally, it'll be on a Thursday. I'll reappear at the coast. Okay. Now, so now, new chapter, new problem. Numerical differentiation. So the problem to consider in this case is given a function f of x and a point x naught, approximate f prime at x naught, or higher order derivatives. So f double prime x naught, and so on. I'll be spending most of the time on the first derivative, but the idea is readily carry over to higher order derivatives. Now, presumably we all know how to compute derivatives, although the midterm gave me pause about that. What about so if all of you, when computing derivatives, can simply use whatever differentiation rules you have, product rule, quotient rule, chain rule, etc. Why not have software do that as well? So we do have software that implements known differentiation rules, for like Maple, Mathematica, also the symbolic toolbox in MATLAB, which really is an interface to Maple, so it's the same thing. So there are many products out there that do this, but there are drawbacks. So first of all, whoops, not sure what happened there. We might not even have a formula for f of x. So your function, all your knowledge about the function f of x might consist of nothing more than pairs, ordered pairs of points in this graph, x values, y values, just like for interpolation, where we're given discrete data and we find a polynomial that passes through those points. So if you don't even have a formula for f of x, you certainly can't apply those differentiation rules to it. In fact, the differentiation rules that I'll be showing you today are based on what we've just seen, where you take your discrete data, fit a polynomial to it, and then you can take the derivative of a polynomial exactly. So presumably, if the polynomial is a good approximation of a function, then the derivative of a polynomial should be a good approximation of a derivative. Now, that's not necessarily the case every time, but it's a philosophy that we're going with. So that's one drawback, and that is, wait. Oh, sorry, my section headings got out of order here. Let me fix that. Okay. Another drawback is implementing these differentiation rules in software does not cater to a computer's strengths, which is just doing arithmetic all day long, bazillions of floating point operations. With derivatives, there's a so for what is called symbolic differentiation, which is actually using the differentiation rules we know, must use complicated data structures, lots of storage, memory movement, etc. You have structures called expression trees that represent the structure of a function. And when you take derivatives, for instance, using product rule, quotient rule, those structures get even more complicated. So it's differentiation rules is a nice way for us to take derivatives, but not for a computer. Besides, if you have a representation of a function that describes its structure, in terms of products and applying other functions, arithmetic operators, etc., you can use that structure to infer what the derivative is without too much trouble. But then you have to optimize that. So suppose you have part of your function is a constant. So you take its derivative and it's 0. So now you have this 0 sitting there in your structure, and you have to prune that out because it's something that's not needed. But rarely do you get an expression that is optimal. Software is capable of simplifying expressions like we do, but you can't get everything. So this optimization, that's something we take for granted when we simplify expressions, is something very difficult to implement perfectly in software. Okay, so instead of working with a formula, we're going to use whatever data we have about f, its values at selected points, and use that to approximate a derivative, and we can do that quite accurately. So we're willing to put up with a certain amount of error in exchange for doing a lot less work. Okay, so it's often done in numerical analysis. A little bit of accuracy to gain a lot of efficiency. That certainly is the case here. So differentiation is what I'm getting into now. This chapter 9, will deal mostly with integration. Now, in Cal 2, you saw that working out integrals is more difficult than derivatives. And the same is true numerically, so we're going to spend a lot more time on that. Okay, so there are two ways to come up with methods for approximating derivatives. One involves Taylor expansions, and the other involves Lagrange interpolation. Now, it will yield the same result, the same formula to approximate a derivative, but we'll contrast both approaches as we go. So, first, before I get into either approach, so a general idea is that, given equally spaced points, fx naught, f and x naught plus or minus the lower plus or minus jh, where j is lowercase j, okay. We approximate f by a polynomial passing through these given points, take the derivative of a polynomial exactly. Okay. And so we could use either Taylor polynomials or Lagrange polynomials. Either one will work. So I'll show you both approaches. Okay, so what I'm going to do is I'm going to illustrate this by stepping through an example. Find an approximation of f prime x naught using these points, fx naught, fx naught plus h, and fx naught plus 2h. And also find the error in the approximation. Okay, and this goes to example in a text, but I'm going to work through the whole thing. Okay. So what we do is Taylor expansion. So we have 2 points we need to Taylor expand. Okay. So first we have fx naught plus h. Okay. So we'll have that's equal to f of x naught plus f prime x naught h plus one half f double prime x naught h squared. Okay. And 1 over 3 factorials, that's 1/6 f triple prime x naught h cubed. And I'll go out to one more. 1/24 f fourth derivative. Remember that notation means derivative. At some unknown point, h to the fourth. Okay. All right. Then I will repeat with f of x naught plus 2h. All right, so h gets replaced by 2h throughout. Now, so here we'll have 4h squared, but that would simplify to 2h squared altogether. So I'll just get rid of this fraction here. Okay, here we have 8h cubed over 6. So that's going to be 4/3 h cubed. And then here I have 2h all to the fourth. So that's 16h to the fourth over 24. So that's going to be 2/3. And actually, I'm going to name these unknown points. They are different in each Taylor expansion. So I'm going to call them C1 and C2. Okay. So now, the form of the approximation is f prime x naught is approximately C0 f x naught plus C1 f x1 plus C2 f x2. Oh, sorry, f x1 is x naught plus h, and x2 is x naught plus 2h. Okay, so the idea is to substitute these Taylor expansions into here and here, and get a system of equations that we can solve for our unknowns, C0, C1, C2. So, okay, actually going to make this equation array. Okay. So in fact, what I'll do is I'm going to say, instead of being approximately equal, I'm going to say it's exactly equal plus error. Okay. So what will happen is I'll dump all these in here, sort out, get approximation of f prime of x naught, and that will appear here. Anything that's left over after simplifying as much as we can, that'll be our error. Okay, so now things get to be a little bit of a mess. Okay, I'll still have C naught f of x naught and C1. So in here, in these square brackets, I need to dump the first Taylor expansion. Okay. All right. And then of C2 plus, okay, so this second Taylor expansion I will dump in there. Okay. So now what we do, sorry, what? Okay. Oh, the power of h, I forgot to grab that. Okay. Sorry, my hearing is awful. I need you to speak up, or I'm just not going to hear you. Or be like that's what it sounds like. Okay. All right. Oh, here too. Same thing. H to the fourth. Okay. All right. So now, in order to get some handle on, we need equations that help us nail down C0, C1, C2. So right now we're grouped by C0, C1, C2, which isn't helpful. What we do is we rearrange the terms and group by f of x naught, f prime of x naught, f double prime of x naught, and so on. So if we look at all the terms multiplying f of x naught, we have C0, C1, C2. So okay, so f of x naught times C naught plus C1 plus C2. In fact, in any differentiation rule, f of x naught is going to be multiplied by the sum of all the unknown coefficients. Okay, now do the same thing, f prime of x naught. Now here we're only going to have two terms. So it's going to be C1 times h, and then they're going to have C2 times 2h. And then I have f double prime x naught. And so what happens here, I have f double prime, we have 1/2 c1 h squared. H squared over 2 c1. Bless you. And then c2, we have 2 h squared. Okay. Actually, I'm going to rearrange this for consistency. So I have hc1 and 2hc2. Okay. Now, we want all this to equal f prime of x naught plus some small error. So, before I even go any further, because I do have more terms, but this should be 0. So we have no mention of f of x naught in our rule. This should be 1. Because f prime of x naught is what we're trying to approximate. We have f prime over here, we should have f prime over here. Plus some error. Okay. And then what we have here is okay. This part should also be 0, so that f double prime of x naught is eliminated. Now, here, that gives me 3 equations. This equals 0, this equals 1, this equals 0. On my 3 unknowns, c0, c1, c2. That's going to determine c0 and c1 and c2 uniquely. So what about my next terms in my Taylor expansion? Well, that's going to involve f triple prime of x naught. So that's going to be okay, f triple prime x naught. Okay. So what we have here is okay. Anything multiplying f triple prime of x naught. So I have 1/6 h cubed times c1. So, whoops. Wait, something's off here. Oh, this editor's being stupid again. So h cubed over 6c1 plus whatever's multiplying f triple prime here, 4/3 h cubed 4h cubed over 3 c2. Okay. Now, because notice here, this expression right here, I want to be equal to 1. So what we can tell right off the bat is that c1 and c2 are going to be of the order h to the minus 1, because they're both multiplied by h to get 1. So, and c0, and because c1 and c2 are going to be something over h, c0 will also be something over h, just so they can sum to 0. So that's true in general, that if you're trying to approximate the first derivative, your coefficients will be something over h. If your second derivative is over h squared, and so on. So since c1 and c2 are order h to the minus 1, this whole thing is order h to the minus 2. And what follows is terms of order h to the fourth derivative. And I'm not going to repeat those here, because really our error is going to come from this. Because I can make this 0, I can make this 1, I can make this 0. I have no control over this, because c1 and c2 will already be determined. So, so what's going to have to happen here is that this is going to be my leading error term. Everything else, I'll have something that's order h to the fourth times c1 or c2, which is order h to the minus 1. So what follows is order h cubed. Okay. So, all right. We're trying to approximate f prime. This term is of order 1. This is of order h. This is of order h squared. Next is order h cubed. It always works like that. Okay. But the thing to do now is solve a system of linear equations for C0, C1, C2. So I can summarize that system of linear equations here. So I have C0 plus C1 plus C2 equals 0. So that comes from here. And then I have HC1 plus 2HC2. Stop it. Equals 1 from here. And then this has to be 0, so that's going to be, well, since this whole thing is 0, I can drop the h squared. I can divide both sides by h squared. So I can have c1 over 2 plus 2c2 equals 0. So based on this, I should have h squared this equation also. Again, divide both sides by h squared. So it simplifies things a little bit. Okay. So really what I can do is, I can ignore C0 for the time being. I have two equations for C1 and C2. So I can solve those. And then plug them, substitute them back in here, knowing that all the coefficients must sum to 0. And get C0. Okay. So trying to so as far as solving this system is concerned, from the last equation, we have C1 is equal to minus 4 C2. Just from rearranging this. So now I can substitute that in here. So from a second equation, I have minus 4HC1 or C2 plus 2HC2 is equal to 1. So I can combine like terms and get minus 2 is equal to 1. So now, so C2 is equal to minus 1 over 2H. Okay. Okay. All right. And now I can multiply that by 4. Or minus 4, and I get C2 is equal to 4 over 2H. And then from the first equation, all coefficients must sum to 0. So if I add these together, I get 3 over 2H. Okay. So I get C0 is minus 3 over 2H. Okay. So does anyone have any questions about how these coefficients were obtained? All right. So Taylor expand whatever points other than f of x0, dump the Taylor expansions in, group by f prime, f double prime, etc. Set everything equal to 0 except for what you're trying to approximate. That should be equal to 1. You get a system of linear equations that you can solve. Okay. Notice, so the coefficients will always have h to the first power in the denominator. Okay. So now, so this will drop out. This will become f prime of x naught. And then this will drop out also. Okay. Oh, I need to put in, since I had it on every other line, error that goes here. So now what I need to do is, to get a hold of a leading term in my error, I need to substitute C1 and C2 into here. Okay, so error term is going to be f triple prime x naught times, so C1 is, okay, so it simplifies to 2 over h. So I have h cubed over 6 times 2 over h, and then I have 4h cubed over 3 times C2, which is minus 1 over 2h. Okay, so that's what I have here. So now what I need to do is simplify all of this. So first, I have h squared to get rid of the h. I have 2h squared over 6, so that's h squared over 3. The 2's in the numerator. I have a minus. I have h squared, which gets rid of the h down there. And then 4/3 times 1/2 is 2/3. Okay. All right, so now this simplifies to minus h squared over 3. And I want to check something here. Okay, plus. Okay. So the error really is of order h squared. We have lower order terms here that I won't deal with. But notice how that plus error is equal to 0. So the error is really the minus of this. So the error is h squared over 3 f triple prime times order h cubed. Often be expressed differently as h squared over 3 times f triple prime at an unknown point, and then nothing else here, because that would also work. Okay. All right. So from the terms in a Taylor expansion that don't cancel, we can arrive at an expression for the error. We can at least see what the order of accuracy is. Generally, if you use 3 points to approximate the derivative, then your error would be order h squared. Whereas like if you use 2 points, it's order h. If it's 4 points, it's order h cubed. So however many points you use, the power of h, again, most times, not always, most times will be 1 less. What can happen is you might be able to get away with using fewer points if you have some nice symmetry. That leads to a higher order of accuracy than expected. Okay. All right. Now, this is what I've shown here. Okay, so let me state the approximation. Is really f prime x naught equals, so I have 2h in the denominator, and upstairs I have, filling in my coefficients, minus 3 f x naught plus 4 f of x naught plus h minus f of x naught plus 2h. Okay. And okay, really it's approximately equals. in this case. So filling in the coefficients we got, that's our numerical differentiation rule. Notice it only uses information about f to the right of x naught. I didn't use like f of x naught minus h or minus 2h. Only points to the right. Notice also the coefficients sum to 0. They will always sum to 0 in any numerical differentiation formula. And the reason for that is, suppose f is a constant. Then I could factor that constant value out of this, and what do I get? I get the sum of the coefficients. Well, the derivative of a constant is 0. So that sum should be 0 to be a worthwhile differentiation rule law. If you can't even get a constant function right, then what good is it? Thankfully, I've seen no such rule. Okay, but there are other numerical differentiation schemes that can be derived using Taylor expansion that I did not mention here, but I really should point them out because they're most commonly used. It's just I wanted an interesting example that would be more helpful to you guys for the homework. Okay, let me zoom in here. Okay, this one right here is the forward difference. And you may recognize this expression, f of x naught plus h minus f of x naught over h, from where? Where do we see this? Yeah, the definition of a derivative, the difference quotient. And this is first order accurate. The error is proportional to h to the first power because only 2 points are used. Now, if you replace h with minus h throughout, you get this one, backward difference. So this uses 1 point to the left of x naught. Notice the errors are the same except for the sign. So it's also first order accurate. So then what you can do is you can average these to get another approximation. Here, the centered difference. So it uses f of x naught plus h, f of x naught minus h, but not f of x naught itself. And what's interesting is, here we benefit from these errors being of opposite sign. If we average them, the errors cancel. So, okay, I actually work out the formula for the error right here. So notice it's order h squared. Even though it only uses 2 points, that's one of the exceptions I mentioned. It's because of the symmetry. So really what happens is you work it out using x naught plus h, x naught minus h, and x naught. It's just that the coefficient of f of x naught turns out to be 0 because of the symmetry. All right, so forward and backward difference, first order accurate, center difference, second order accurate. So these are the most commonly used numerical differentiation methods because they're very simple. They just only use the value of f at 2 points. And this one in particular gets a very accurate approximation of that error being order h squared. Okay. So here's an example. Here I have a made-up function. I'm sure that nothing like this occurs in nature. I hope not. And I take the derivative using my Cal 1 skills. It's pretty awful. So imagine having a computer evaluate that. It would revolt. So I plug in 0.25, I get this value. So now I just use the center difference. Now this expression is still ugly, but not nearly as ugly as this. So I just evaluate this at only 2 points to the right and left of 0.25, spacing of 0.005. And this is the approximation I get compared to the exact value. So here's the error, 10 to the minus 4. Something that in many applications would be considered perfectly acceptable because there's often uncertainty in whatever model you have anyway. So a whole lot less work to get that level of accuracy. Okay. Yeah, here is the approximation I just stepped through. What I did here in the book was actually factored of 1 over h out of the approximation, so that C0, C1, C2 would just be numbers. In retrospect, that's probably a better way to present it, but I just didn't think of that here. Okay, but you get the same result that is second order accurate. Okay, so that's one approach. Okay. And here in the text I discuss how to do this more generally, and that leads to this problem, which I did not assign. So I'm going to show you a function, this function, make diff rule. Oh, you can use that in 721, Sarah. So, yeah. So I can post it because I didn't assign it. So what does this function do? I need to make this a lot bigger. Fonts. Okay, so this function, you give it several indices. There are multiples of h. So for example, if I was doing this in a previous example that I just showed you, I'd pass p equal to 0, 1, and 2. So f of x naught plus nothing, f of x naught plus 1 times h, and f of x naught plus 2 times h. So actually, I'll run it first so you can see what I'm talking about. Okay. All right, so if I do make diff rule 0 to 2, so that's a vector 0, 1, and 2. So what I get is minus 3 halves, and then 2, which is, so this would correspond to the minus 3 over 2h. This would be the 4 over 2h, and this would be the minus 1 over 2h. So we're assuming h is 1, and we get the coefficients. So this spits out those coefficients for you. For the homework, you'll be writing a function that computes these coefficients, but using Lagrange polynomials, which I will get to in a moment. But what this function does to get those coefficients is we're setting up a system of linear equations. However many points you have, that's how many equations you have. And the right-hand side will be all zeros, just as I had in the example, except for the second row. No matter how many points you have, you want the first derivative, the second element on the right-hand side needs to be 1. So that's what I do here. And then I fill in the coefficients. So whatever element I have in my vector p of multiples of h, in row L, I raise it to the Lth power. And I fill my matrix with that. Now you can kind of see that in here. This row, first row, I have all my multiples of h raised to the 0 power, but anything to the 0 power is 1. So we always get 1s in the first row. Second row, we have my multiples of h, multiples of h raised to the first power, 1 and 2. And then here, normally I would have my multiples of h raised to the second power, so you think I have 1 and 4. Now I don't have that here, except if I multiply the equation on both sides by 2, I'd have c1 plus 4c2 is equal to 0. So it's equivalent to what's in the code. It's just scaled by a constant. That's because of Taylor's theorem. That has a factor of 1/2 in that term. So this is a matrix that this code is making. It's just that the rows may be scaled differently. And then I just solve a system. So this is MATLAB's way of solving systems of linear equations. A is your matrix, B is your right-hand side vector, A \B computes the solution. Something we'll deal with a whole lot more in 461 for the very, very, very few of you who will go on to that, as I'm seeing in SOAR. Okay. So that's how. So this works for for whatever indices. So for example, I'll run this again. if I use -1 to 1, so I'm using f of x naught plus h, f of x naught, and f of x naught minus h. And I get 0 for the coefficient of f of x naught, so f of x naught is not needed. And I get 1 over 2h and minus 1 over 2h. That's the center difference that I showed you earlier. Okay. So in problem 915, you make a function like this and use Lagrange polynomials, so you can use this function I just showed you to check your answers, because they should be the same. Okay. Now, how do you do the same thing using Lagrange interpolation?
I have a question.
Yes.
Can you please go in the Taylor expansion you did V2 order 4?
Yeah.
But you said we needed just 3 points. So couldn't we have stopped at that 3?
Yes, I just made a guess as to how far to go.
Okay.
Yeah. And I figured that would be far enough. So actually, in the text, I did do that. But here's something interesting that happened. This is what I got for the error term. And the thing is, normally I'd like to use the intermediate value theorem to justify combining these. But because they have different signs, I can't. So there's actually an advantage to going out one more term to see what that coefficient really is. The coefficient really does work out to be what we get here. It's just that you can't use the intermediate value theorem to justify it. Whereas when I did the same thing with the center difference, I get these error terms, but I'm taking this minus this. So these terms have the same sign. So I can use the intermediate value theorem to justify combining them into one term at one unknown point. But the other approach, Lagrange interpolation, makes it easier to get these error terms. So approximate f prime of x naught using Lagrange polynomials. What you do is you keep in mind that f of x is approximately equal to a sum. So if you're using n plus 1 points like we have been, f of x naught, or x of xj, times Lagrange polynomial at x. So if I keep that in mind, then f prime of x naught is approximately, so I can take the same sum, whoops, where I will take the derivative of Lagrange polynomial and evaluate it at x naught. So all you have to do is, okay, so from there, to get the coefficients, Cj, so like C0, C1, C2 from a previous example, compute Lagrange polynomials for points being used, take their derivatives, evaluate at x naught. Okay, so in MATLAB, you can obtain Lagrange polynomials using the MATLAB function polyfit with y values, dang it, equal to all zeros except 1 that equals 1, because that's the definition of Lagrange polynomial, or main properties, like this came up on a test, that the Lagrange polynomials are equal to 0 at all the interpolation points, except at one of those points are equal to 1. So you can use polyfit, you specify x's and y's. So you pass in your x values, and then use your for y values, just use all zeros and except for a 1. And you can use polydir to take their derivatives, and polyval to evaluate at x naught. Now, more specifically, whoops, something went wrong there. Okay. So in the case of equally spaced points, where you have x minus k, actually I want to use the same notation as in the book. Okay. All right, so x minus j, xk, where xi is equal to x naught plus ih. So in other words, I have x minus jh over here, x plus kh over here, and every point in between at spacing h. So what you can do is can interpolate at the integers minus j to k, and so these serve as your interpolation points, and can evaluate derivative of Lagrange polynomial at 0, because 0 corresponds to x naught. Basically, what we're doing is a change of variable to make all that work. Okay. So what I'll do is, okay, time is short. Okay. I wonder if I have any discussion about this. Okay. I have something worked out in text, but I don't like how this looks. Okay. So using the same points, x naught plus h, x naught plus 2h. Okay. Okay. Form Lagrange Lagrange polynomials for points x equals 0, 1, 2. So how this will work is, okay. At x naught, so my first Lagrange polynomial. Now I'm going to, due to time, I'm going to cheat here. But I'll show you how this works. I want to use for my x values 0, 1, 2. My y values for first Lagrange polynomial will be 1, 0, 0. And since I have 3 points, the degree of my Lagrange polynomial is 2. Always 1 less. So those are so that's my polynomial. 1/2 x squared minus 3/2 x plus 1. Okay, so that's x squared over 2 minus 3x over 2 plus 1. So therefore, its derivative is going to be x minus 3/2. So I get my coefficient. I evaluate that at 0. And I get, so I plug in x equals 0 here, and I get minus 3/2. Which is just, so remember the coefficient I got from, for this point before was minus 3 over 2h. So you just remember to put the h down in the denominator. Now I do the same thing at x equals 1. So I have, so the second polynomial, and I'll go back to MATLAB. And now I put a 1 in the second position, and I get minus x squared plus 2x plus 0. So I get minus x squared plus 2x. So its derivative is going to be minus 2x plus 1. So at, no, that's not right, 2. I plug in x equals 0 into the derivative, and I get 2. In the example before, I had 4 over 2h, so 2 over h. And then lastly, x equals 2. So this corresponds to x naught plus 2h. All right, so now I'll do this again for 1 in the third position. And I get 1/2 x squared minus 1/2 x. So I get, okay, x squared over 2 minus x over 2. And I take its derivative, and I get x minus 1/2. Plug in x equals 0, and I get minus 1/2. So those are the same coefficients as when I derived the same differentiation rule using Taylor series. Okay. All right. Now, okay, so really, just to indicate what goes with what here. Okay. All right, so that's how you can derive these same rules. But what about error? How do you handle that? Turns out the error in Lagrange interpolation is helpful with that. Okay, wait, I went too far. Okay, so what happens is, if you take the formula for error in Lagrange interpolation, and you take its derivative and plug in x naught. I won't go through a process here, but it boils down to this. Your exact derivative is equal to this approximation, so that's what I just derived, and then this right here is your error. So notice this part comes from a formula for polynomial interpolation error, so that doesn't change. Then you have these linear factors, but no, before it was x minus x naught, x minus x1, etc. But now x naught is substituted for x. And you don't have x naught minus x naught because 0 is skipped. That comes from taking all those linear factors, that product linear factors, and taking a derivative using a product rule and plugging in x naught. It boils down to this. So one of the homework problems is, what happens to this error formula if the points xi are equally spaced? I'm not assuming that here, but if you do, then you can actually work out what this is. This simplifies dramatically. And what you can do in a homework problem is, when you work out what this is, when the points are equally spaced, so spacing h, you can check your error formula that you get against the many examples in this section, like these two right here. Okay. Actually, this is a formula that one of the homework problems is to derive this using Taylor series. Okay, so So here we don't have any issues because of the intermediate value theorem. So one of the nice things about Lagrange polynomials compared to Taylor series, in certain cases it's easier to come up with the error formula than with Taylor series. Another point I'll quickly make is, what about higher order derivatives? The approach doesn't really change. So like if you're using Lagrange polynomials, instead of taking the first derivative of Lagrange polynomial and plugging in x naught, you'll take whatever derivative you want. So I'm trying to get second derivative, I would take L double prime and plug in x naught or 0. You can use Taylor series, but so what would happen is, for example, suppose I was using these same points to approximate the second derivative. All of this would be the same until I got down to here, and I would set this equal to 0 and this equal to 1. So the 1 would move down. So your system of equations, whatever derivative you're trying to approximate, that has a 1 on the right side. All other right-hand side values are 0. So what that means is, since this is supposed to be 1, that means my approximation for a second derivative will have an h squared in the denominator. And that's what we have here. This is the centered difference for f double prime. So it uses these 3 points, and notice the h squared in the denominator. And notice the error, it's second order accurate, just like the centered difference is for the first derivative. And then here's another for the second derivative using the points I used in the example. It's coincidence that the coefficients are the same. But there are quite a few formulas out there for like, I have examples for first derivative. Like here's one that uses 5 points for a first derivative. So it uses x naught and plus h, 2h, 3h, and 4h. And that's fourth order accurate. Whereas this one uses f of x naught plus and minus h and plus and minus 2h. 4 points, because we don't need f of x naught because of a symmetry. Also fourth order accurate. So generally, the more points you use, the higher order accuracy you get. Although, if your function is not well behaved, like it has oscillatory behavior, then you might find yourself in for a letdown as far as the accuracy you get from these higher order approximations. So you have to be careful about that. Okay. I'll do some mop-up on numerical differentiation on Tuesday, and then I'll start the basics of numerical integration. As far as the homework for differentiation, okay, it had previously October 29th, which is this coming Tuesday. It's Halloween, because I figured it was scary enough. Okay, and I'll adjust these as we go. But, okay, so if you have any questions about the test, shoot me an email or get in touch with me somehow.